So we just saw 4 examples of linear transformations that, you have to admit, were very easy. So you could solve the matrices in your head by just picturing what the unit vectors were doing, right? So let's go to a real complex example, okay? So this will be problem 7. So in problem 7 asks, transformation that defines the projection into a line. Consider the projection of vectors into the line y equals mx. Write down the associated matrix. What does this mean? So let's picture it. Consider the projection of vectors into the line y equals mx. What is the line y equals mx? So that's a line that crosses the origin and has a slope of m. Yes, so let's say m equals 2. So then the slope is equal to 2. So we have a line like this. Yeah, so this would be y equals 2x. Yeah, so this is the case when m equals 2. What does it mean, consider the projection of vectors into this line? What this means is that if you have any vector v, we want to find the transformation which projects the vector into the line. So we want to find this projection. So this is 90 degrees. So we want to find this vector. This will be the transformed version of v. So we project it into the line. Yeah. If we consider a vector like this, w, then we want to project it again into the line. So this is 90 degrees. So we end up with a vector like this, a of w. Okay, so that's what projection means. But we don't want to do it for the case m equals 2. We want to do it for the general case, right? So this is where the complexity starts. So how do you find an equation for the projection of a vector into a line? If you remember from last chapter, yeah, so chapter 1, vector spaces, we saw a recipe for projecting a vector into a subspace. Yeah, and if the subspace is a line, that's very easy because this subspace is the span of one single vector. Yeah, so let's say that our line, let's say that we can write our line y equals mx as the span of a unit vector e hat. Okay, so let's imagine we can find this vector e hat. How do we project a vector v into the direction of e hat? Yeah, so there was a way for calculating this projection here, the projection of v into the direction of e hat. So this vector was equal to the inner product of v with e hat, and this will be a scalar number multiplied by e hat. Yes, this was the recipe. By the way, you also had an alternative recipe, which was v inner product with vector e divided by inner product of vector e with itself times vector e. And this works when e is not a unit vector. But if e is a unit vector, so the length of e is 1, then this becomes easier. And that's clear because the bottom is equal to 1. Yeah. Okay, so then if we could find this vector e hat, which is the unit vector in the direction of the line given by y equals mx, then we could project any vector that we want. For example, we could project x hat and y hat. Why do we want to do that? Because we ultimately want to find a matrix, and this matrix wants to be the projection of x hat as the first column and the projection of y hat as the second column. So our aim should be to find these two columns, right? Therefore, the first column will be the projection of x hat, which will be the inner product of x hat with e hat times e hat. That will be the projection of x hat into this line. And the second column will be the inner product of y hat with e hat multiplied by e hat. So we are almost there. The only thing we're missing is finding e hat, the unit vector in the direction of the line that we want to do the projection to. So we need E hat. How do we find E hat? So let's imagine we have our x and y axis, and we have our line y equals mx. Yeah. So let's try to find a vector in this line. So a vector like this. How do we find such a vector in general for any value of m? Well, we know that this line has a slope m, right? Therefore, we know that if we move to the right, what does the slope mean? If we move to the right 1 unit, then we move up by m units. Yeah, that's the definition of slopes. Therefore, we could say that this vector, let's call it E, is equal to 1 to the right, so 1x hat, plus m up, my hat. So is the vector 1m. So this is a vector included in this line. Is it done? Are we done? Can we substitute E here into these two equations for x hat and y hat, and then substitute the results into the two columns? Well, not quite, because we want a unit vector, E hat, for this recipe to work. Remember, this recipe worked only when the vector was an orthonormal basis. In this case, the basis is only one vector because we are working with a line. But it has to be orthonormal, meaning that the norm of vector E has to be 1. So we have a vector whose norm is not 1. So let's find vector E hat. So vector E hat is the normalized vector, the normalized version of this vector E that we found. So how do we normalize a vector? We divide by its length. Yeah, that's how we normalize a vector. Yeah, and what's the length? So this will be E divided by the length of E, which is the square root of 1 squared plus m squared. Yeah, so that's it. That's our vector E hat. So E hat is equal to 1 divided by 1 square root of 1 plus m squared times vector E, which is 1m. And this is the vector E hat, which in our drawing, it would correspond to a vector. Let me use another color. For example, a vector this, that has a unit length, yeah, and this would be E hat. Yeah? So we scaled vector E down. Okay, so that's our E hat, which we can now substitute into our recipes. So let's do it. So A of x hat is equal to the inner product of x with E multiplied by E. Since we are talking about real vectors, the inner product becomes the dot product, right? So this will be x dot product E hat. I mean, we could do the conjugate, but since E is a real vector, it doesn't matter. So we don't need to do the conjugate, yeah, in the direction E hat. So what's x dot E hat? So if E hat is this vector here, if we do the dot product with x, that's like getting only the x component, yeah? So this will be the x component of E multiplied by E hat. And the x component of E is 1 divided by the square root of 1 plus m squared. And then we have to multiply this by E hat. Remember, the recipe has an E hat here. So we are carrying it forward. So this is equal to 1 divided by the square root of 1 plus m squared times E hat, which is 1 divided by the square root of 1 plus m squared times 1m. So we can multiply these two square roots and we end up with 1 divided by 1 plus m squared times vector 1m. So that will be A of x hat. So this vector, which is a column vector, yeah, so this vector is 1 divided 1 plus m squared and m divided 1 plus m squared. This will be the first column in our matrix. Okay, great. We are almost done. We have the first column, which means we have this column. Now we need to look for the second column, which is the transformed vector version of y hat. So I don't have much space, so I will do it much shorter. So this is equal to y dot e hat in the direction e hat. So it's going to be very similar procedure. So we are going to get m divided by square root of 1 plus m squared. That's y hat dot e hat times e hat, which is 1 over square root of 1 plus m squared times 1m. So if we write it as a column, this is the same as the previous vector, but with an extra factor of m. So this will be m divided by 1 plus m squared and m squared divided by 1 plus m squared. And this will be our second column. So now we have the second column, which goes here. So how does the total matrix look like? So our matrix A is equal to, we can actually take a factor of 1 plus m squared outside because it appears in every single term in the matrix. So we can take it outside of the matrix. So we can write here outside 1 plus m squared. And then inside the matrix, we write the first column, which is 1m, and the second column, which is m squared. And this finalizes the problem. This is our matrix that projects any vector into the line y equals m times x. Let's check it. So I have prepared the applet to check this. So notice here I have this matrix, which is 1 divided by 1 plus m squared, and then the matrix 1m, m squared. This is the matrix that we found. And on the right here, I now have a slider for m. So for example, right now m equals 2. So if you substitute the 2's, you see they are substituted now, you end up with this matrix. So using this matrix, you can check, you can multiply it by any vector, and the result is, so we start with the yellow vector v, and the result is the projection onto the line y equals mx, y equals 2x, which is this blue vector here. Okay? So you can see that it is indeed projecting the vector into this line, whatever vector we choose. But now we can change m, and when we change m, we are changing the matrix. So let's say m equals 0. So now the matrix is 1 divided by 1, 1, 0, 0, 0. So we end up with this matrix. And this matrix indeed projects any vector into the x-axis. Yeah, you can see that. So this matrix works for any value of m. It always projects the vector into the corresponding axis, into the corresponding line. So it worked, and that was a little bit trickier, right? But notice how easy everything has become once you find the matrix for the projections. Yeah. So now projecting a vector into a line becomes a multiplication times this simple matrix here. So thank you very much for watching. See you later.